I welcome you for the second lecture on earthquake resistant design of foundation for NPTEL online course. As we discussed in the first lecture, there are 5 modules for this course, and the first module was on introduction, which we have already covered. Today we are going to start the second module, which is on the shallow foundations, and this module will have 5 chapters which are shown in the slide here. First of all, general requirements, bearing capacity and settlement, combined footings, raft foundations, and dynamic bearing capacity. So, today we are going to talk the first chapter of this module, that is the general requirements. And under the general requirements, first thing, types of foundations, basic criteria for design, terminology, and modes of soil failure. So, these will be discussed under this chapter 1 of the module 2. Let us talk about first type of foundations. You know that when we talk about the foundations, there are 2 dimensions. One is the width of the foundations and another is the depth of the foundation. If width of the foundation is more than the depth of the foundation, then we treat it as a shallow foundations. However, if it is other way, that means if a depth of a foundation is more than the width of the foundation, then we say it is deep foundation. Under the deep foundations, we have further 2 categories. One is moderately deep foundations. If the ratio of depth to the width is less than 15, but naturally more than 1, then it is called moderately deep foundation. However, if this ratio of depth to width is greater than 15, then it is deep foundations like pile foundations, well foundations, caissons. So, this is the like general classification based on the depth and width of the foundation. We treat shallow foundations. Choice of foundations depends on the requirements, and it is not easy because it depends on many factors. It will depends on the type of loads coming, it will depends on the type of soil, and it also depends on your objective for which the foundation is designed. However, for the regions of economy, the first choice for an engineer for foundation is shallow foundation, because given the same situation, the shallow foundations is more economical compared to other types of foundations. Therefore, as far as possible, one should use the shallow foundation even when earthquake loads are considered, provided that shallow foundation is adequate. If we find that shallow foundation is not adequate, then only we go for other types of foundations like piles, piers, wells, and other things. Before we discuss the shallow foundation in detail, let us see the different situations where you have different types of foundations. So, you could see in this slide that there are 6 situations A, B, C, D, E, F. In the first case, when we see for A case, you have this dense sand which is going up to great depth. For B case, instead of sand, we do have clay, and that is also going to up to great depth. And the third case, you have soft clay up to great depth. So, on all these situations, and before the soft clay, on the top of it there are stiff clay up to 3 meters. So, in these 3 situations, normally shallow foundation may be okay for the normal loads, but if the loads are excessive, unusual, and if you have the earthquake loads, then we may require deep foundations depending on the severity of the loads coming. Then if we see the case D, E and F, and in for D case there is a soft clay up to 15 meter and then it is situated on the rock, while for the E case up to 6 meter there is a soft clay, but it is underlain on medium dense sand which is extending quite deep. In both the situations deep foundations are required because you have soft clay in both the cases up to quite depth. So, if we compare D and E with A, B and C, then you could see the difference is that the condition of the soil. So, because in A case sand was dense, in B case clay was stiff, and in C case you do have stiff clay up to 3 meter. But when we see D and E cases, then you do not have any dense sand or stiff clay. As a result, we need to go for deep foundation. When we consider the F, which is loose sand up to great depth, in that case we need to use a raft, or we need to densify the soil, or we need to go for the piles. So, out of 3 options, whether raft foundation, densification or pile foundation will be required in this case. Continue with this, we do have other cases given here. You see G, then H, I are there. So, for the G, the situation is like that, you have soft soil up to 8 meter depth, then medium up to 16 meter and then firm. So, 16 meter is quite deep. So, because it is up to 8 meters, it is soft clay. So, we need to use raft or friction piles. In H case, it is compact sand up to 3 meter, then another 3 meter medium soft clay. So, what we do, we require drilled piers or cast into piles. Then you have another situation where you have 3 meter, 6 meter and then going, and then gradually you have compact glacial fills. So, the conditions are not good. So, in that case again the pile foundations driven or cast into piles are required. Wherever you do have the rock in this case J, so on the top of it rock you have miscellaneous fills, dense sand and firm clay. In this case again we require piles, while in this case K, which is up to 12 meter soft clay, then medium dense. So, piles or piers are required, and then finally in case of L, which is miscellaneous fills and loose sand up to 5 meter underlain on the rock, we require end bearing piles or piers. So, in general, seeing all these cases, one can see that what type of foundation is required. That depends on the type of soil first of all, in which type of soil, even for the same loads, but many times even if the type of soil is same, but loading conditions are different. If you have the heavy loads, then the foundation gets changed. As for earthquake load are concerned, first we go with the shallow foundation, and among the shallow foundations also we do have different categories, different types of shallow foundations. So, for example, when you have the stiff footing, or stiff footing is that type of footing where L is quite length of the footing is quite more than the width of the footing. That means you have a continuous footing maybe on that. So, that is a straight footing, and you do have isolated footing where you have separate footing for under a column. So, you could see that there is one column and then this is isolated footing. Then we do also have what is called trapezoidal combined footing. In case of trapezoidal combined footing, you do have that footing under the two columns has been combined to each other, which can be seen in the slide, and this could be either rectangular or trapezoidal. In this case it is trapezoidal. Then you could have rectangular combined footings, which is given in this case, and finally it could be either mat or raft foundations. So, basically if I separate it out, one category is you have strip or isolated footing, second trapezoidal combined footing, and third one is raft foundations, and all these we will discuss in detail during this course. Now, the relevant codes which are related to this course are given here. You have IS 1904, which is a code of practice for design and construction of foundation in soil, general requirements, and this is published by Bureau of Indian Standards, New Delhi. Then you do have another code 6403, which was first published in 1981 and reaffirmed in 2002. That is a code of practice for determination of bearing capacity of shallow foundations, again published by BIS. Then there is Eurocode 7, that is basically on geotechnical and related to the shallow foundations. So, that is also relevant for this course. Within the domain of shallow foundations, there are different terminology which is required while going for the design of foundations, and those terminology which we are going to discuss. We do have what is called gross pressure or gross loading intensity, denoted by QG as shown in the slide. This could be defined as pressure due to weight of the superstructure, self weight of footing, and weight of soil. So, that means it consists of all combined weights from the top of the footing, coming from top, and you have superstructure, then below that you have footing, and below that you have the soil. So, combined jointly all the three weights, total weight will give you the, and divided by the area where you will give the loading intensity. So, gross means it will include all. Then we do have the net pressure or loading intensity, which is Q subscript n, and that is if we exclude the weight of the soil coming on the footing, then that is the net pressure or loading intensity, which you could see in this figure. Actually, as for depth of foundation is concerned, it is from the ground level. What you could see here, you could see is here is the ground level, this is the ground level, and this is the base of the footing. So, the distance between the ground level and the base of the footing you do have is df, and this df is nothing but it is called depth of the footing. So, whatever weight of the soil inside this df will be minus gamma df, and once you do have subtract that, then you get net pressure or loading intensity. Then third one is called ultimate bearing capacity, which is QU, and when we talk about ultimate bearing capacity, this is the minimum gross intensity of loading that the soil can support before the failure in the shear mode. That means, this is the, in other words, if I say that this is the maximum permissible value, because if you go beyond that, then your soil will get failed in shear mode. So, this is the this gross intensity which we can have. Now, continue with this, there are more terms which are defined, that is net ultimate bearing capacity QNU. Again, to find the net ultimate bearing capacity, we subtract the weight of the soil column, which is minus gamma df. So, QNU minus if I see that QNU minus so QU minus gamma df is the value of QNU. Then for design purpose, instead of net ultimate bearing capacity, we required what is called safe bearing capacity. So, there is a difference between ultimate word and safe word. So, if you see safe word, here it is ultimate word as used. So, once we say safe, then we need to divide the value of QNU, which has been obtained in 0.4, by a factor of safety Fs. So, once we divide this factor of safety Fs, then we get the value of QNS, and naturally the value of the factor of safety cannot be less than 1 typically for the foundations this is taken between 2.5 and 3. So, for this without earthquake the minimum value of recommended of factor of safety is 2.5, but while considering the earthquake load the value of factor of safety may get reduced. Then the last one is called the safe bearing capacity, which is QS. If we add the weight of the soil column again to the net safe bearing capacity, then what is called as safe bearing capacity, and this safe bearing capacity is also called popularly QS is also called in short SBC. So, safe bearing capacity. So, this SBC is very popular and SBC is given by this relation which is here, and you could see that this is QNS plus gamma df, that means QNU divided by factor of safety plus gamma d. Here one thing to be noticed that under gamma df there is no factor of safety is used because this pressure is added in full. So, this is the final equation to find the safe bearing capacity from this. But in this equation you could see that the value of QNU is given by QU minus gamma df, where gamma df is known to you. So, if we are able to get the value of QU, then we can find the safe bearing capacity. So, our ultimate objective is now left out, that to find the value of QU. So, in the next slide we are going to give the answer that how to find the value of QU, that will be our objective. So, for that first let us see that how soil gate failed in different modes of soil failure. So, for that purpose what you have that modes of soil failure, you have for horizontal strip footing which is resting on the surface of homogeneous soil and subjected to gradually increasing load, then let us discuss the characteristic load settlement curves. So, you know that when we conduct some test, then we can get the load settlement curve from the some test, for example plate load test. So, once you conduct the plate load test for this the settlement curve or the like can be found using what is called plate load test, and which is called in the short PLT. Using PLT the curves which has been shown in these figures can be here. You can see that this is like given in this figure. So, the load settlement curve for 3 different situations A, B, C. Now, let us see that what is in these different scenarios. If you have the general shear failure, and the general shear failure is the case when you have the very dense soil, for example dense sand or which is behave like a brittle type material. In case of general shear failure, what I could observe that there is a kink here, you could see that this point. So, load settlement curve have a particular kink and after that it get changed, and if we see the failure pattern is suggesting that there are bulging of the soil at the surface, and this is applicable for very dense sand or stiff clay. When we talk about the second mode of failure which is called punching shear failure, in case of punching shear failure you have which is applicable for highly plastic soil, you could see there is poorly defined failure pattern, it is not like this. Here we do not have kink like which is shown in the first part A, you have only a smooth curve, and the third one is called local shear failure. Local shear failure is the condition between general shear failure and punching shear failure. So, this occurs mostly in medium dense or firm straight. You could say you have well defined ways, but you do not have the well defined pattern which has been seen. So, if I see the curve of load settlement of the third case, it lies almost between the A and B case. So, in A case you have the kink, in B case you do not have. Here you have this higher load for the same value of settlement here compared to the B, but you do not have the clear kink which is shown in case of A. So, depending on the type of soil, it may undergo either general shear failure, local shear failure or punching shear failure. Punching shear failure occurs mostly in the organic soils, which is very poor soils. So, those types of soils are not allowed for the foundations. So, as a result, later on either we may go for that either for general shear failure and the local shear failure, and we avoid the punching shear failure. So, that will be our objective. Now, let us first discuss how to deal with this case, first case general shear failure. Once we have this, we are done with this, then we will come to the local shear failure. And this slide, before we go ahead, let us see, this shows that how the relative density affect the modes of soil failure. In this figure, you could see that on x axis there is a relative density, while on the you have on y axis the ratio of the depth to width, which is ranging from 0 to 5 and 10. What you could see that when the relative density is more than 70%, you have the general shear failure, but when the relative density is less than 70% and more than 30%, then you do have the local shear failure zone, while when the relative density is less than 30%, then you have punching shear failure zone, as and said that punching shear failure is avoided. But there is a effect of depth also. For the same relative density, higher the depth, then you come under the category from general shear failure to the local shear failure zone. So, that but when we do have higher the depth, then you are aware that it is going for the not for the shallow foundation, it is going in the different category. So, that is why that will be discussed later when we discuss about the deep foundations. Now, before we move to this how to find the bearing capacity and other things, let us see that what are the basic criteria for design. And for the design, we do have first criteria is location and depth criteria. Irrespective of the loads or type of soil, there is a minimum, bare minimum depth of the foundation, and that depends on the general conditions of the site, that we need to select the depth of foundation such a way that its performance is not adversely affected by factors such as lateral expulsion of soil, seasonal volume change by freezing etc. So, in that case, and the bare minimum depth of foundation is 0.5 meter. So, even if you are constructing a boundary wall which does not have carrying much load, its height is very small, like even if it is not much height, still we need to use minimum 0.5 meter. So, it can be said that minimum depth is here, minimum is suggested is 0.5 meter. So, 0.5 meter is the case, and when the loads increased, then naturally the value of this depth of foundation need to be increased further. The second is bearing capacity criteria. When you design your foundation, suppose your foundation is rectangular, then design means what is the depth of the foundation and what is the width of the foundation. Then bearing capacity, it should be such that dimension of the foundation or footing should be such that it is safe against shear failure with an adequate factor of safety. What is a factor of safety, which we have already discussed, and adequate means here typically the factor of safety should be in the range of 2.5 to 3. Then one of the most important criteria is settlement. If your footing or foundation is safe in the bearing capacity, it does not mean that this is fine, rather we need to apply the check for the settlement, and you have seen in the first lecture that due to the large settlement or excessive settlement, the buildings got tilted in Japan during the Niigata earthquake. I have shown you the slides during the Niigata earthquake, and a classic example of the settlement is the worldwide is the Pisa's Leaning Tower. Pisa's Leaning Tower is a geotechnical settlement problem, where the building got settled due to the excessive settlement. So, when we talk about settlement, there are differential settlement, then you do have the total settlement. So, differential settlement should be minimum and naturally within permissible limit, and differential settlement is normally a fraction of total settlement. So, we need to reduce the total settlement, but the differential settlement should be totally avoided, and limits for differential settlement is going to be lower than the total settlement. So, this is regarding the basic criteria, and with this I thank you for this chapter 1 for the module 2.